the 5th lesson of the second term. Welcome. We're dealing with work, energy, and power. So our focus is on the concept of power. Okay, power is the rate at which the work is done. Power is denoted by P, and mathematical, we have P equal to W over delta T, which is the rate of work. It is also given as the rate at which the energy is transferred, which means we have P equal to E over delta T. So P is denoted by P. It is a scalar quantity, and it is measured in watts. Let's consider here the first example. It says a car maintains a constant speed of 110 kilometers per hour on a straight level road. The total resistive force acting on the car is 750 newtons. We need to calculate the work done against friction over a distance of 10 kilometers. Okay, let's do that together quickly. Okay, example number 1. Okay, 1.1. Let's check what we have. We have a force, frictional force of 750 newtons. We have a displacement . What is the displacement? We have a displacement of 10 kilometers. You can write it as in meters. 10 times 1,000 is 10,000 meters. So friction is acting in the opposite direction because it's a resisting motion. Displacement is forward. The angle in between is 180 degrees. Okay, so we can use this formula, W equal to the force times displacement cos of theta. We substitute the force is 750. Displacement is 10,000. And theta is 180 degrees. Okay, let's make calculation. We get negative 7,500,000 joules. Okay, in megajoules, which is the same as 7,5 megajoules. Okay, 1.2. We need to calculate. Okay, let's go to the question together quickly. Okay, 1.2, we need to calculate the power output of the car. Okay, the power output of the car. So let's check what do we have. We have V, the speed is 110 kilometers per hour. We can divide it by 3,6. We get 30,56. Or what you can do, you can say V is equal to 110 times 1,000 meters, because in a kilometer we have 1,000 meters, divided by in an hour with 3,600 seconds. Then we get this answer, 30.56 meters per second. Okay. Then you can use this formula. P is equal to F, the force times the speed. Okay, power output now will be the same as 750 times the speed, which is 30.56. So let's calculate 750 times 30.56 is the same as 22,920 watts. Okay, that is the power output of the car. Okay, question number 2. Let's go back to the notes. Horses were once used to raise water from coal mines. Given that an average horse can lift a load of 750 kilograms at a speed of 4 kilometers per hour, calculate the power output of such a horse. Okay, so let's check what do we have. What do we have for number 2? We have the speed, which is 4 kilometers per hour. We convert is the same as 4 divided by 3.6, which is 1.11 meters per second. What else do we have? We are given the mass, which is 750 kg. We also know G is 9.8 meters per second squared. Then we can make substitution. P is equal to the force times the speed. The force now is mg, which is the force required to lift the mass, times the speed. Let's substitute. The mass is 750, G is 9.8, and the speed is 1.11. Okay, let's make calculation. 750 times 9.8 times 1.11. The answer is 8158.50 watts, which is 8,158.50 watts. Okay, let's go back to the questions. Okay, so we're done with that one. Example number 2. A lift comprises an electric motor, a cage, and its counterweight. The counterweight moves vertically downwards as the cage moves upwards. The cage and the counterweight move at the same constant speed. Refer to the diagram below. Okay, you can see we have a motor, there we have the counterweight. This is the counterweight, and we have a cage on the other side. The cage carrying passengers moves vertically upwards at a constant speed, covering 55 meters in 3 minutes. The counterweight has a mass of 950 kg. The total mass of the cage and passengers is 1,200 kg. The electric motor provides the power needed to operate the lift system. Ignore the effects of friction. Okay, let's go to the questions. Define the term power in watts. Then 2.2, calculate the work done by the gravitational force on the cage. Calculate the counterweight, calculate the work done by the counterweight on the cage. 2.3, calculate the average power required by the motor to operate the lift arrangement in 3 minutes. Assume that there are no energy losses due to heat and sound. Okay, let's do this together. Example number 2. Two point one, the term power. Power is the rate at which work is done. Or we can say power is the rate at which the energy is transferred. 2.2.1. We need to calculate the work done by gravity on the cage. So you can say W is equal to F delta X cos of theta, which is the same as mg times delta Y cos of theta. The mass of the cage is 1,200 kilograms and G is 9,8. The height covered is 55 meters. Cos, let's check. Gravity is acting downwards, but the cage is moving upwards, which means delta Y is upwards. So the angle in between is 180 degrees. Let's calculate 1,200 times 9,8 times 55 cos 180. The answer is negative 646,800 joules. That is the work done by gravity. So it's negative 646,800 joules. Let's go to the second question. We need to calculate the work done by the counterweight on the cage. 2.2.2. The work done by counterweight on the cage is the force times the displacement cos of theta, which is mg delta Y cos of theta. The mass, the counterweight is pulling with its mass, which is 950. It is pulling the cage with a mass of 950. The distance is 55. Cos. Now, the cage is pulling downwards, and the distance covered is downwards. So, which means the angle is 0. Let's make calculation. 950 times 9,8 times 55. Cos of 0 gives us 512,050 joules. Okay, 2.3. Okay, let's go back to the questions. We need to calculate the average power required by the motor to operate the lift in 3 minutes. Okay, so we have the average power, which is the same as the work over delta T, the rate at which the work is done. Average power is equal to the rate at which the work is done. Okay, so what we know, work net is equal to 0 because the system is moving at a constant speed. Then the work net is the same as the work done by gravity plus the work done by counterweight plus the work done by the motor, which is equal to 0. The work done by gravity is negative 646 800 plus the work done by the counterweight, which is 512050, plus the work done by the motor, which is equal to 0. We make the work done by the motor to be the subject of the formula, which is 134750 joules. Then we substitute it into this equation. Then we get the average power of the motor. The time, now we have T in seconds. Delta T is 3 minutes, in seconds is 180. So the answer 134,750 divided by 180 gives us 748,61 watts. That is the power. Let's go back to our notes. Example number 3. A motor pulls a crate of mass 300 kg with a constant force by means of a light inextensible rope running over a light frictionless pulley as shown below. The coefficient of kinetic friction between the crate and the surface of the inclined plane is 0.19. So you can see that the system. The first question is to calculate the magnitude of the frictional force between the crate and the surface of the inclined plane. The crate moves up the inclined plane at a constant speed of 0.5 meters per second. 3.2, we need to calculate the average power delivered by the motor while pulling the crate up the inclined plane. Okay, let's do it together. This is example number 3. Point 1, we need to calculate the friction, the same as mu times the normal force. Okay, let's draw the free body diagram. So the block is pulled up by, let's call it F by F. We have a gravitational force acting downwards. We have a frictional force acting opposite. We have the normal force acting perpendicular to the plane. Then we have the component of gravity acting here. And this is the same as 25. This is mg cos 25. If we remove the applied force there, the object is going to slide with the component of weight, which is mg sine 25 degrees. Okay, any other force acting? Okay, that's all. So now we can substitute mu, which is the coefficient of kinetic friction, is 0.19. Okay, times what is the normal force? The normal force is the same as mg cos 25 degrees. Then you can substitute the mass is 300. G is 9.8. Then cos of 25. Okay, let's calculate product to get friction of 506.26 newtons. 3.2, we need to calculate the average power of the motor. So if we have P equal to V, the product of the velocity and the force, of P equal to the force times the average speed. Now we need to calculate F. F net is equal to MA, which is equal to 0 since the object is moving at a constant speed. Now we have F, which is the force applied by the motor, minus mg sine 25 degrees minus friction is equal to 0. Then we can take everything to the right. Then we have mg sine 25 minus the frictional force. So the mass is 300, g is 9,8, sine 25 degrees, minus we've calculated the frictional force, which is 506,26. Then we can get the answer here, which is 300 times 9,8 sine 25. Okay, friction will also be positive, plus 506,26. So what is the answer? The answer is 1748,76 newtons. Now let's substitute this into this formula. With P, which is equal to F times V. So what is the force? Is 1748,76 times the speed is 0,5. Okay, the answer 1748,76 times 0,5. We get the answer of 874,38 watts. Okay, that is the power. Let's go back to the notes. Okay, we've calculated the average power delivered by the motor. Learners activity number 1, please do this by yourself at home. An electric motor drives a water pump which is submerged at the bottom of a borehole that is 8 meters deep. Calculate the minimum power of the electric motor required to pump water at a rate of 21 liters per minute. Calculate the minimum power output of an electric motor which is used to pump water at a rate of 13,3 kg per second from a borehole 13 meter deep. Number 5, a water pump rated at 2 kilowatt is claimed to pump water from a borehole 30 meter deep at a rate of 50 liters per second. Determine if this claim is reasonable. Then activity number 2, a windmill is used on a farm to pump water out of a well that is 37 meter deep. The water flows past point A, which is 37 meters above the well, to the dam with a constant velocity of 2 meters per second. Okay, you can see the diagram there. Questions? Calculate how much energy is required to pump 90 kg of water out of the well to point A. If it is necessary to pump 90 kg of water per minute, what is the maximum power that the windmill must produce? The farmer wants to modernize the farm. He decides to buy a 0.5 kilowatt petrol water pump. Will the petrol water pump be able to produce the required power? Give a reason for your answer. Why would you advise the farmer to rather use a windmill instead of a petrol pump? Okay, that is the end of the lesson. Thanks for taking part of the lesson. All the best. Learn, grow, and succeed. Thank you very much.